Have you ever wondered how scientists know if some liquid is a dangerous acid or a super strong alkali without, touching it or tasting it? Well, today we're going to be chemical detectives. We're going to uncover the colorful secrets of something called pH. Okay, let's just dive right in. Okay, just look at this. This is what happens when concentrated sulfuric acid gets a hold of plain old table sugar. It just erupts into this black, charred column of carbon. It's a pretty dramatic way to show that, yeah, some chemicals are incredibly reactive. They're dangerous. You can't just go around tasting or smelling things to figure out what they are. And that presents a pretty serious problem.
So that leads us right to the central mystery we're solving today. How in the world can we tell if a chemical is a corrosive acid or a caustic alkali without any of the dangerous stuff? There's got to be a safer way, right?
And that question, given what we just saw, is definitely a dangerous one. We need a really smart and, more importantly, a safe way to answer it. And the answer? It's actually pretty clever. It's something called a chemical indicator. Basically, an indicator is a substance that does all the risky detective work for us. It changes color to let us know if it's sitting in an acidic or an alkaline solution. It's like a secret code, a visual clue to an invisible world. So let's start with the absolute classic, the one everyone's heard of. Let's talk about the litmus test.
The beauty of the litmus test is its simplicity. The rule is super straightforward. If you're dealing with an acid, a blue litmus strip will turn red. And if you have an alkali, a red litmus strip will turn blue. It's a basic yes or no test. Is it an acid? Is it an alkali? That's it.
So what's actually going on here at a level we can't see? Well, acidic solutions are packed with these things called H+ ions. Those are what make the blue litmus turn red. Alkaline solutions, on the other hand, they're full of OH- ions, and those do the exact opposite, turning the red litmus blue. It's kind of like a tiny chemical tug-of-war. But here's the catch, and it's a big one. A weak acid like lemon juice will turn litmus paper red, but so will incredibly powerful hydrochloric acid. The test tells you if it's an acid, but it gives you zero clue about how strong it is. It's missing a huge piece of the puzzle. So that limitation is a real problem. We need to move beyond just a simple red or blue answer. It's time to look at a much more advanced tool that gives us a way more detailed picture. And here it is, the universal indicator. Now we're talking. Instead of just two colors, this stuff gives us an entire rainbow. And this whole spectrum of color lets us see not just if a solution is an acid or an alkali, but also its strength. Now we're getting some real information. And you don't even need a lab to see this kind of thing in action. Nature has its own indicators. Just look at red cabbage juice. It turns pinkish red in acidic orange juice, stays kind of purplish in neutral water, and then goes green or even blue in alkaline baking soda. It's a fun little kitchen chemistry experiment you can do yourself. All these color changes, they're all pointing to one fundamental measurement. And that brings us to the heart of the matter, the pH scale. This is the system that takes that whole rainbow of colors and turns it into a simple, elegant numbering system. The best way to think about the pH scale is as a ruler for acidity. It runs from 0 all the way up to 14. 7, right in the smack dab middle, is totally neutral. Think pure water. Anything with a number below 7 is an acid, and anything above 7 is an alkali. So let's just lock this in. If the pH is less than 7, you've got yourself an acid. If it's exactly 7, it's neutral. And if it's greater than 7, it's an alkali. Simple as that. This scale gives us a precise number for what those indicators were showing us with their colors. And here's the really crucial part for understanding strength. It's all about the extremes. The farther you get from that neutral number 7, the stronger the substance is. So a pH close to 0 means a very, very strong acid. And a pH way up there near 14 means a very, very strong alkali. Okay, so we've covered the science, but why does any of this matter outside of a chemistry lab? Well, it turns out pH is all around us. It's influencing our world in ways we barely even notice. I mean, just take a look at this chart. That lemon in your fridge has a pH of around 2, super acidic. Milk is just a little bit acidic, pretty close to neutral. And then way on the other end of the scale, that heavy-duty oven cleaner you've got under the sink, it's got a pH of about 13, which makes it extremely alkaline and very caustic. And here's a beautiful example of how nature uses pH. The color of a hydrangea flower is literally a direct indicator of the soil's chemistry. Gardeners know this trick. They can actually change the flower's color from blue to pink just by tweaking the acidity of the soil it's planted in. How cool is that? And this isn't just about pretty flowers. In farming, getting the soil pH just right is absolutely critical for growing healthy crops. Farmers will literally add alkaline stuff to the ground to balance out soil that's too acidic. And it gets personal too. The pH of your shampoo and your skincare products is carefully designed to work well with your hair and skin. So, all this leaves us with a final thought to chew on. If just a tiny little shift in pH can completely change the color of a flower, what other invisible changes is it causing all around us, every single day, in our bodies, in our food, in the environment? It's definitely something to think about.